It is now 2:01 p.m. So it's time for us to get going. Today we're very fortunate to have Asenjo-Garcia from Columbia University as our speaker. Are you sharing your screen, Anna? Can I not see it?
I can share. Yeah. Give me one sec.
Okay. So Anna did her undergraduate work at the Universidad Complutense de Madrid. I speak French, not Spanish, so please excuse how I demolished that accent. And she was a grad student there and also at ICFO in Barcelona before moving to Caltech as a Marie Curie postdoc and recently moving to Columbia. She is a real superstar and expert pioneer in this area of understanding collective sub and superradiance of atomic ensembles. This idea that our concept of independent emission, spontaneous emission of atoms can really break down, and this can change the nature of quantum optics rather fundamentally. So I'm really looking forward to the story that she's going to tell us today. Let me point out before we go any further that you can enter questions in the Q&A and also on the YouTube live stream, and we will address them during several breaks during the seminar. And let me also remind you that there will be a discussion with Anna afterwards. So with that, Anna, take it away.
Thank you so much, John, and thank you everyone for inviting me to give this seminar. I'm really excited. So I apologize beforehand because I have some crazy cats and they might interrupt this, but hopefully everything will be seamless. So today I'm going to talk about single field and many photon physics in 1D atomic arrays. And in particular, I'm going to kind of present our work on how 1D atomic arrays are very versatile and tunable light matter interfaces. Well, let's see if this works. Yeah, okay. So there is a fundamental question in quantum physics that is how to control quantum systems and prevent decoherence. And in the context of quantum optics, this question takes a bit of a different form. That is, how can we realize control atom-photon interactions? So control or efficient atom-photon interactions are important for many realizing many ideas in fundamental science, such as, for instance, if we want to realize quantum nonlinear optics, or many body physics between atoms that is made by photons, or between photons made by atoms. It's also crucial for understanding out-of-equilibrium phenomena. And of course, it has, or it's crucial for many applications. If we want to develop efficient quantum information processing tools, or if we want to develop quantum networks, want to measure better, or if we want to realize quantum simulation or even quantum computing, these control atom-photon interactions are a key element. Okay, so this works, that's good. Okay, so I want to just, for kind of the sake of comparison with condensed matter systems, give an overview or what are the differences between a photonic system or an optical system and a more traditional kind of, let's say, quantum matter. So in the case of an optical system, everything happens at a finite frequency. And in particular, a very important distinction is that photon number is not conserved. So if we have, for instance, a copper wire and we put a potential difference, the electrons will move. And if we shine now a laser into a fiber, we will have a similar transport of photons, now again at a given finite frequency. But the difference is that if we have a defect, for instance, close to this surface, this photon can be radiated away. Because optical systems are inherently open, it's very different from the typical condensed matter system where we cannot imagine that the electron is gonna suddenly jump into vacuum. And while dissipation can be detrimental, it can also be a tool because it allows us to control and get information from our system. That's what happens in optics. But there is an inherent conflict between control and dissipation. Okay, so this is the first, I think, in my opinion, one of the main differences between condensed matter systems and optical systems. There is another clear difference, that is that photons do not interact with each other. And so that's very different from the typical electronic system. So to make photons interact, we have to interface photons with matter in the form of atoms or other kind of quantum emitters. And so taking into account these two important points, oh my God, okay, now it works again. One can think of like, what are the key ingredients for realizing an ideal light-matter interface? And one ideally would like to have a light-matter interface that is strongly non-linear, such that photons interact with each other, and this would enable applications, for instance, for quantum information processing, and at the same time where dissipation, even if it exists, it is controlled, okay? Fine. So we can think about what kind of platform could this be. So the first attempt one can think of, choosing is very simple. The minimal one is a single atom. So a single atom, at least when we approach it as a two-level system, is strongly non-linear. And so if a photon comes and it's absorbed because of the anharmonicity of the potential, basically a second photon is prevented from being absorbed. So it is strongly nonlinear, that's good. But what is bad is that it decays, it has a finite lifetime. And when the photon, when the electron goes back to the ground state and the photon is emitted, this photon is emitted in a quite broadly manner. And this is related with the second issue, that is that atom-photon coupling in free space is weak. So this means that if we have an atom and we shine some laser beam into it, the probability of this photon that is basically in this optical mode to interact with the atom is very small, and is basically related with the ratio between the absorption cross-section of the atom and the mode area. And because of the diffraction limit, this is a very small value. Okay, so it looks like we have to go beyond a single atom. So what is next? What can we do? So how can we increase atom-photon interaction? So back in, I don't know, many decades ago, Purcell told us that the decay rate of an atom depends on its environment. It's not something that is intrinsic to it. It depends on what is around it. So the most obvious way to change this decay rate that is related effectively with the coupling between atoms and photons is to change the environment. So let's change it. So imagine that we have an atom in a vacuum in free space. So free space has a density of optical modes, and because the atom is in vacuum and it can feel this, the presence of these optical modes, basically it acquires this finite lifetime, and basically this is translated into the atom having a spontaneous emission rate that is gamma zero. And this gamma zero is proportional to the imaginary part of the Green's function in free space. So this is the propagator of the electromagnetic field, and is something that is determined by the environment. Okay, so this is fixed if we are in vacuum, but what happens when we put other structure next to the atom? So we just, for the sake of it, we can choose a COVID-19 virus, we can place it close to our atom, and the atom will feel its presence via these optical modes, and it's gonna change the decay rate. And in that case, the change in the decay rate happens because the Green's function, the propagator of the electromagnetic field, has changed, okay? So while I think this is a potentially doable experiment, I would expect that the lifetime doesn't change very much, because I guess a virus doesn't have a very large refractive index. So being realistic, what is the actual solution is to place an atom close to a dielectric structure, so close to a cavity or close to a waveguide, and thus the development of the fields of cavity and waveguide QED. So when we put an atom into a cavity, the probability of the atom decay into the cavity mode is enhanced. And basically how efficient is matter interaction is given by the figure of merit called cooperativity. That is a ratio between the photon being emitted into the cavity mode, that is what we can control at the rate gamma c, and again emitting it into free space and losing it. In waveguide QED, we have a similar figure of merit, and that's called the optical depth. And this is again a ratio between decaying and emitting a photon into the 1D reservoir versus emitting it into free space. Okay, so I wanted to show you some figures of merit of different systems that people have employed to enhance atom-light interaction. So a common one is to use or to trap atoms close to a fiber. In this case, the basically optical depth is not very large, it's around 5%. So the probability of decaying into the fiber guided mode is small. You can do a bit better. You can use a photonic crystal. So a photonic crystal is a dielectric structure with a periodic modulation of the refractive index. And this allows this structure to have a band gap where light cannot propagate, but close to the band gap at the band edge, you have very slow group velocity. So as the photon propagates, it can interact very strongly with the atoms. It has a lot of time. So this is translated into a large or a larger efficiency in the interaction between atoms and guided photons. People have grown basically quantum dots in photonic crystals, and this has yielded larger efficiencies. And as far as I know, the highest efficiency in light matter coupling right now is that found in superconducting qubits in transmission lines that is of the order of 100. So it's extremely large. So is that everything that dielectric gives us? Is just a way of enhancing light matter coupling? Can we do just what people can do in cavities, but on a fiber? The answer is no. A waveguide allows to do many more interesting things. And what are those things? So one example is that, for instance, here, if we place an atom close to a waveguide and we send a photon, if this atom is strongly coupled to the guided mode, it can reflect the photon perfectly. So a single atom can behave as a perfect mirror, and you can build a transistor out of this. Another example is that, as I've mentioned, in photonic crystals, there is a band gap. And this means that one can tune the interaction range between atoms trapped along a photonic crystal and make it either dissipative or coherent. This means switching off dissipation in the coupling between the atoms through the guided mode of the photonic crystal. And other options that are enabled by these dielectrics is, for instance, chiral quantum optics. So in chiral quantum optics, what you're doing is you benefit from the intrinsic helicity of the near field of dielectric. And basically this helicity couples with the polarization of an emitter. So, you know, it has selection rules. So you can have, for instance, an atom that has excited state that decay to the ground state, emitting either circularly polarized to the left or to the right photon, or a linearly polarized photon. So if you select a given transition, there is basically a spin orbit coupling, which means that photon that is emitted and has sigma plus polarization will only propagate towards the right, and with sigma minus, it will go the other way. So this unidirectional propagation allows to realize, for instance, cascaded systems. And it's, for instance, a tool to realize cluster states, which are a way of realizing measurement-based quantum computation. So this means that interfacing atoms with dielectrics is not just a way of, you know, doing better cavity QED. It's a way of doing different things. It enables a lot of possibilities for atom-photon physics. Okay, perfect. And then the question is, then it means that we are bound to do this. We have to interface atoms with dielectrics. Isn't this right? And the answer is that no, you actually can do all this just with atoms. So if instead of a waveguide, you place a kind of impurity atom close to an atomic array or an atomic chain, you can realize the same type of physics. And this is what I'm going to talk about today. So in particular, atom arrays, when the distance between the atoms is small, and I will define what small means in a bit, they support the states that do not radiate or decay due to interference in photon emission. And this means that when this impurity atom decays, it's gonna transfer its excitation to the atoms in the array, And this excitation is going to propagate in a polaritonic manner in this atomic waveguide. And although I haven't, or I won't talk about this today, dark states are interesting because these are states that are naturally protected from dissipation. So one can leverage them, harness them to build better quantum memories and to improve the signal to noise ratio atomic clocks. Okay, so why is this relevant now? The answer is that there has been amazing progress in realizing atom arrays with optical tweezers. So now I would say it's almost quite doable or accessible for many experimental groups to realize defect-free 1D, 2D, and even 3D order arrays, at least 1D and 2D. In these systems, if, as I've mentioned, if the atoms are close enough to each other, interference in how photons are absorbed and emitted is going to lead to correlations between the atoms, and then the atom arrays can behave as quantum nanostructures. So this has been already shown for the first time, actually, as far as I know, this year. So this year, there have been two very beautiful experiments. So the first one was produced in the group of Emmanuel Bloch, where they have shown that if you place, basically, if you shine a light into a 2D atomic array, this 2D atomic array is going to behave as a perfect mirror if the distance between the atoms is smaller than the wavelength of the impinging light. So light is going to be perfectly reflected. And this is precisely because of the same phenomena of interference that allow dark states to exist. Another recent experiment has shown collective frequency shifts in light in a 1D array. So this has been performed in a group of Tuambro waves. So these are the first experiments, I think, that show interference effects in how light interacts with atomic arrays. Okay, so I want to discuss what I'm going to talk about today. So basically, I'm gonna explain our work in trying to understand these atomic waveguides. So I'm gonna talk about single and few photon physics in atomic chains. And then I will change gears, and instead of harness the dark states to guide photons in these atomic chains, I'm gonna talk about superradiance. So what happens when you put many, many excitations in these atomic chains? Okay, so just very briefly, I wanted to discuss how to, what's the theoretical treatment. I think my neighbors just decided to build something, so I apologize. I just want to discuss what is the theoretical approach to deal with this problem. So imagine you have an ensemble of atoms. They can be ordered, disordered, it doesn't matter. And when light is impinging into the atoms, it's going to induce a electric dipole moment. And now this means that these atoms are going to be now emitters, and they're going to radiate this field. And there is going to be interaction that is mediated between photons, between these atoms. And these photons basically can be integrated out. And this is totally fine in vacuum. And what remains is that eventually we'll find a Hamiltonian, or actually more complicated like Lindblad operator, that will depend on just the atomic degrees of freedom. And the interactions will be mediated by this, which is the electromagnetic Green's function that, as I've mentioned in the beginning of my talk, is determined by the environment. So very briefly, what we find is an atomic density matrix that evolves according to a Hamiltonian and a Lindblad operator, because this is an open system, so there is dissipation. And this is how we capture this. And so the Hamiltonian has a part that is going to tell us about the coherent evolution, and is related with the real part of the Green's function, so the propagator of the photons between atom I and atom J. And the Lindblad part has basically is proportional to the imaginary part of the Green's function, and this accounts for collective dissipation. An interesting thing is that it depends on which are the positions of these spins of these atoms. Okay, so that's why it's collective. So I just want to remind everyone that this is a many-body system, so the dimension of the Hilbert space 2 to the n. So in principle, it can be arbitrarily almost complicated. So what we're going to do is, instead of looking at many excitations, we're going to look at what happens when we have a single photon in our array. So in that case, we can describe the system in a simpler way. We can look at, we can describe it via a non-Hermitian Hamiltonian, which is written here. So this is the same Hamiltonian as before, but I have included both the real and the imaginary part of the Green's function here. And this is in vacuum, so the propagator of the electromagnetic field is given by this expression here. And so, okay, now I have a Hamiltonian that describes this spin interaction in a 1D array. And this means that trivially, for an infinite chain, I can diagonalize this Hamiltonian in the single excitation manifold using block waves. It's very easy. So now we're going to have these states, these spin waves, where basically that have associated a wave vector in the z direction along the direction of the chain. And these spin waves are going to have a dispersion relation. So some energy, some frequency. And because it's an open system and the Hamiltonian is not Hermitian, they are going to have also some given decay rate. Okay, so there are going to be spin waves that are radiative, which are what we call superradiant, and they're going to have a finite lifetime. And there are spin waves that are completely dark, subradiant, and will live forever if our array is infinite. Okay, so here it is. So if the distance between the atoms is smaller than half of the free space wavelength, the atomic resonance wavelength, then we have dark states that emerge and they are protected from decay. So let me explain what this means with respect to this dispersion relation. So this is a dispersion relation that tells me the energy of a given spin wave with wave vector kc relative to the atomic resonance frequency and normalized to the spontaneous emission rate in vacuum. And this is the wave vector, basically is the Brillouin zone of basically my chain. And so I have a region in my Brillouin zone that is what is called light cone, where modes that are radiative can live. So these modes will decay because they have a wave vector and an energy that is compatible with photon emission in free space. If we cross this light line, we find that we have this, all these modes, basically, or all this dispersion relation. That means that here what happens is that we have a wave vector that is much larger than any wave vector that a photon in free space can have, which means that photons can propagate along the chain, but in the transversal direction, they are evanescent. So they are truly guided photons that cannot escape. It's not allowed for them, basically. And these are the subradiant or dark states. So, okay, if this is true and these atomic arrays support dark modes, can we harness them to build waveguides out of them? And can we couple impurity qubits to them and make these waveguides mediate interactions between them as we did using the electrics? So as I've said before, Purcell already told us that the decay rate of an emitter depends on its environment. So now I'm gonna have this impurity qubit and it's gonna couple to, it's gonna be in the presence of this environment that is vacuum modified by the presence of the atomic waveguide. So now this atomic waveguide is a bath for this impurity. And what we can do under the Born Markov approximation, and I'm happy in the questions to discuss when this is doable, we can integrate out this atomic array. And this is gonna lead to a modified emission rate of the impurity qubit that now can decay and the photon can propagate as a polariton in the chain, or it can radiate the photon away at a rate that is slightly modified from the vacuum emission rate because of the presence of the chain. And of course, if this is true for one qubit, it's true for multiple qubits. So this means that these arrays can mediate interactions between impurities. So let's see how one can describe this physics theoretically. So what we can do is, again, calculate the Green's function, which is going to tell us about the lifetime and the coupling of the impurity qubit to the atomic chain. So in general, to calculate the Green's function is a complicated task, but in a 1D array, it is, can be obtained semi-analytically. So it's a very symmetric problem that has cylindrical symmetry. And if it's infinite, then we can obtain an expression that reads like this. So the Green's function, that again is going to be proportional to the, is going to tell us about the decay rate of the qubit impurity, is the vacuum, basically Green's function, modified by the presence of the array. And so basically this tells me that it's an integral over the Brillouin sum of something that basically here are some field eigenmodes, a lot of Bessel functions, it doesn't matter that much. And here we have a dispersion relation. So this means that if we look at this integral, we have to perform it in the complex plane. But the interesting thing is that in 1D, we can separate the emission into free space from the emission into the guided mode, because it's a pole of this integral, which means it's very elegant, and we can find not an approximate or numerical result, but an analytical result. So we can do this. So the decay rate, modified decay rate into the guided mode of the chain, normalized to the qubit spontaneous emission rate, is given by this expression. The important thing here is that, okay, we have some kind of block mode profile of our chain, and we have the group velocity. Why does this make sense? So if we have now, as I've said before, this has a band structure. So the group velocity here is very small, it approaches 0, which means that the decay rate into these slow modes will be very large. So this is why the group velocity has to appear here. And then there is the decay rate into free space, and I can talk about it, but it's just like some integral, so it's kind of more boring and it's harder to get an intuition from it. So, okay, so how do this look like in reality? So again, it depends on if our impurity, where does it sit in the dispersion relation? Is it close to the band edge? Is it at a region where the dispersion is linear? Is it in the band gap? This is gonna be crucial to determine which kind of interactions and decay we can have from our impurity. So these are the results. And I just wanted to show in this slide that basically you can do everything that you can do with a dielectric, you can do with these atomic waveguides. So this is basically this first plot shows the optical depth, which is the efficiency of the coupling to the guided mode against emission into free space. So if this is high, the coupling is very efficient. And so we see that, you know, for, of course, tiny distances, this coupling is extremely high. This is very hard to realize experimentally. So it's probably easier to say that maybe you can get a coupling of the order of 10 or 1 in these atomic waveguides with kind of realistic distances or accessible with current state-of-the-art experiments. So this tells you about, you know, whether this coupling is efficient. So it can be very efficient. And this means that we can do everything I've mentioned before. So for instance, if we have an impurity close to the atomic array and we send a spin wave, this spin wave is going to be perfectly reflected. So the transmittance of this impurity will approach 0 when it's resonance. Sorry, the transmittance of this spin wave will approach 0. It will be perfectly reflected. If now we place multiple impurities, there will be superradiance, and then this basically this transmittance dip, it will broaden because now the impurities are behaving as a macro atom. So this is what happens when spin waves can propagate in our array. But what if now we place the frequency of the qubit in the band gap? So in the band gap, guided modes cannot propagate. And if we place two emitters or impurities close to each other, the only possibility for them is to do a spin exchange, coherent. So this is what we can see here. So this is the population of both impurity qubits that have been coupled to the array. We excite the qubit in red, and after some time, we see that the population is transferred to the qubit in green and back and forth. So this is a typical example of population state transfer due to coherent interactions. There is, of course, a loss because always there can be emission into free space that we are not suppressing. Another example, just to tell you how versatile these interfaces are, is that one can realize chiral quantum optics. So again, because this atomic array has, and the field is confined, there's a near field, which means, there is helicity in the near field, which means that if we place an atom that has the right polarization or impurity qubit that has the right polarization close to the atomic array, it will only emit or mostly emit in one direction. So this is what we're seeing here. So when this QED decays and it has sigma plus polarization, the only side that is mostly populated in our chain is the left side, not so much the right side. So basically this enables all paradigms that I know of in Waveguide QED.
Anna, can I stop you for one moment so that we can get some questions in? Is that okay? Is now a good time?
Perfect time, yeah.
Okay, fantastic. All right, so our first question is from Didi Libfried. He asks, is there an analogy between your single excitation dark wave and a single phonon propagating in a 1D chain of trapped ions?
I would say so. So there are many analogies. So well, I have to say, I'm not sure about, so I could imagine that this is, yeah, very similar to a phonon propagating in a phononic waveguide, in the sense that, you know, it's like one-dimensional and it doesn't decay as it propagates, or it barely decays as it propagates. The part that is a bit harder for me to think is whether, you know, phonons can leak out. And so in our case, you know, we have like all the part of the modes that are superradiant that are really not confined to the chain, and they can leak out. So this would be more similar as if you have a bulk medium and then you would imprint like a phononic waveguide there, but still like phonons could still go outside if they don't have the right wave vector.
Okay, fantastic. Okay, next we have a question actually from Jonathan Conjaman, who asks, if you have multiple species in the array, do you expect acoustic and optical photon branches?
If I have multiple, yes, in principle, well, even if I have if I have multiple polarizations, I will have as many branches as polarizations I have. If I have multiple species, that's actually a good question. I highly doubt that you can have acoustic species that are guided, because I don't think they will have the right wave vector, but I will need to think about this.
Okay, so that I guess actually perfectly brings us to the next question from Alicia Kolar. She asked, does it matter if you use a matter-like waveguide where the free modes have a quadratic rather than linear dispersion, as one would get from a conventional waveguide? I guess this is getting at this idea, could one get analogs of this physics with an array of impurities in a Bose-Einstein condensate or something?
Yeah, definitely. So this is, I think, a very good question. I think one of the interesting things of these arrays is that they are very tunable. So in principle, you can engineer your dispersion relation, or by placing your qubit in the right places, you can get the right, at least region of the dispersion relation. And in principle, you can, I think there are multiple possibilities. I think in 1D, is more constrained, the kind of dispersion relations you can get, but in principle in 2D or 3D, I think it can be wide.
Okay, a really amazing question, actually. This one's from some guy named John Simon. The question is, are there any 2 excitation dark states?
Yes, that's a great question, and also perfectly matches with my next slide. So thanks.
Well, that's fantastic, because that's the last one we're going to ask for now. So please continue.
Yes, so no, definitely there are dark states of 2 excitations, 3 excitations. So basically, you have dark states. Well, it's complicated. So for low density of excitations, you have dark states that are truly dark. So basically, when dark states tend to like to be as very smooth spin waves. So imagine that you have a chain and you try to place 2 photons on your chain, then they would like to, you know, repel each other while at the same time be the most extended possible. And definitely there are these dark states, and actually you can build an ansatz for them. And you can do that by taking a Slater determinant of the 2 most subradiant eigenstates in the single excitation manifold. This is how you build at least part of the 2-photon subradiant states. But imagine that you keep doing this. So now you put 3, and okay, it's okay, 4. And eventually you get to a point where you put so many excitations that they cannot fit in the chain. And then there is no darkness anymore. So the most obvious example is when all atoms are excited. In that case, there is, in that subspace of dimension 1, there is one state that is the product state of all atoms excited. Of course, it is not subradiant. Yeah. Okay, so these are all the questions.
Yeah. Well, always an infinite number of questions, but I think this is a
these
good
are
point.
the selected questions. I see. So you selected your own question. That's smart. Okay.
I mean, I told you it was an amazing question.
Okay. Okay. So then, thanks for your question, because it completely, my slide completely follows, which is what happens when you have, multiple excitations, multiple photons in your array. So what are the physics of this quantum nonlinearity? So in general, when we want to realize nonlinearities in atomic systems, what one does is use EIT. So it makes transparency in the optical medium, in an optically dense medium. And then using Rydberg atoms, one can make these kind of propagating photons interact. So in this case, something similar can be done in atomic arrays, but we do not need Rydberg because already atoms have this hardcore nature where you cannot put 2 excitations on top of each other. Then this is the physics of atomic photon collisions in these atomic arrays. And as I'm gonna just discuss in a next slide, these are tunable. So basically imagine that you have 2 spin waves that are crossing each other. What may happen? So what may happen actually depends on the distance between the atoms. So when the photons start approaching, or these polarities start approaching, this kind of 2 photon repulsion starts to switch on. And what happens is that when they start to overlap, realize that this is a long-range interaction. It's not a local interaction, it's a non-local interaction. So what happens is that they may either collide and explode. So both photons are out of your chain now. And this is what happens actually here. So this is the population, the 2 excitation manifold. Initially, you have population 1, which it's normalized. So it's you have 2 photons. And after this collision has happened, the population has decreased. So this is because there is radiation. And the other possibility that may happen is that the photons cross each other and they do not, leave the chain, and they pick up a phase when they do this. And this is controlled by, at least by the distance in the interatomic distance. And the reason is because when you have a very small distance, your brilliant zone is huge. Okay, so it means that there are many subradiant or dark states, and the light cone is very tiny. So when these photons cross, they distort and they scatter into all wave vectors. But because the light cone is so tiny, then most of the wave vectors into which they scatter, they are dark. And so, this collision is coherent, there is no dissipation. But if now you have a very significant light cone and you control that by, at least relative to the brilliant zone with the distance, then the scattering into the light cone can be huge, and this will produce radiation. So this means that we have this kind of tuning knob to make coherent or dissipative interactions between photons. And in particular, for the coherent interactions, one question that we're interested in understanding, but so far we're getting there, but we're not done, is whether this opens up the potential or the door towards realizing a conditioned phase gate between the 2 photons because of this accumulation of phase. And if you want to read more on, not about this, but if you want to know a bit more on the physics of the few bodies, subradiant states, you can take a look at these papers, which explain this idea of fermiionization and so on. Okay, so then maybe it's time. Well, I wanted to mention that we are not the only ones thinking about this. So there has been recent papers on the archive in the groups of Susan Yelin and Misha Lukin and F. Shamoun on realizing actually using 2D arrays to mediate interaction between qubit impurities. And also a very nice paper by the group of Helmut Ritz on how a ring of atoms can behave as a cavity for this single impurity atom. So these ideas are kind of catching up. Okay, so now I'm gonna change gears and I'm not gonna talk about dark states that much. I'm gonna talk mostly about bright states. And this continues with actually John's question on what happens if you start to pack your chain with many, many, many photons, like what is going on. Eventually we know that, I understand the physics of dark states, and I know that when I have many excitations in an atomic medium, there are things like superradiance, so there has to be a connection between these two things. So this is what I'm going to discuss now. So, okay, so what happens when we have many photons in the chain? So what is the, the understanding of the many-body dissipative dynamics? So as I've mentioned before, large excitation densities do not support dark states. And this is because, like photons cannot efficiently repel each other. So, okay. This means that, as you increase the excitation number, you're going to have more and more bright modes, less and less dark modes. And in particular, when these photons are packed together, radiation is unavoidable. So we don't have this picture of, now we have this kind of cool quantum matter or photonic crystal for photons, and we have analogies with condensed matter system. No, this is really completely different paradigm where radiation is very important. So it's really, really open. Okay, so in the most extreme case, what happens is that where all atoms are inverted. So I have a chain, and even though here I just plotted 5, let's imagine that we have all the atoms excited. So the initial state is that of a product state of all atoms inverted. And so the question is, what are the many-body signatures of collective decay in this situation? It's very different from just single excitation. So the first one that tackled this problem and studied this problem is, of course, decay. And so decay realized that when you place many atoms exactly in the same location, and this has to be exactly the same location, or in a cavity, which is basically the same, one can look at the photon emission rate. And so if the atoms are uncorrelated, like they are not interacting with each other, you would expect that the intensity is radiated in an exponential manner. But because of interactions, what happens is the process of superradiance, where as atoms start decaying, they synchronize and they build up a huge dipole that radiates energy in a burst. And this is the superradiant burst that shows in a peak here in the radiated photon emission rate. So, okay, so this is very well known since 1953, actually. So what is there to do? Well, actually a lot, because what is the physics of this for extended or mesoscopic chains? The question is not as trivial. Actually, Vicky was very smart in choosing a problem that one can solve exactly. In the case of a 1D array, this is not the case. So to do this, I'm going to change a bit the picture. So I'm not going to talk anymore about this like single excitation subspace or non-Hermitian Hamiltonian and so on. I'm going to really harness the full density matrix. And what I'm going to do is I'm going to interpret the decay in terms of jump operators. So now we have the density matrix evolution that, again, like follows Hamiltonian dynamics. In Dicky's case, this term is switched on to 0 exactly. This is not the case in extended arrays or in extended anything. And then here we have the Limblad operator that is now written in terms of collective modes. Okay, so these are these collective jump operators, O, nu, of decay rates gamma nu. So I have n atoms, means I have n jump operators. And these jump operators, I find them as because they are the eigenstates of a matrix of these elements. So it's the dissipative matrix between, how, the imaginary part of the Green's function connects atom 1 with itself, atom 1 with atom 2, atom 1 with atom 3, and so on. But I'm just keeping track of the imaginary part. The real part is embedded in the Hamiltonian. And this is where the geometry is built. So again, the Green's function is the propagator. So it's the part where it's going to tell me whether I'm, this is a chain or is a 2D array or a disordered cloud or a ring or whatever. And so the important thing is that when a jump operator acts on our atomic state, is going to imprint a relative phase between atoms. And the action of a jump operator means that a photon is being emitted, okay? And so the evolution now is basically that of quantum trajectory. So we have a pure state, a wave function that evolves according to a non-Hermitian Hamiltonian. And at random times, there are jumps where, excitation is lost and a photon is emitted. And so I want to raise your attention to an amazingly beautiful paper, that is that paper of Carmichael and coworkers, which I'm afraid to say that I discovered like a month and a half ago. And this physics is explained there, and it's a great paper. Okay, so then let's try to understand the jump operators in the case of a 1D array and how do they look like. So just to give a connection also with something that can be measured, I'm gonna, or I hopefully can be measured like within, current state of the art capabilities. I'm going to depict here an array of 10 atoms. And these atoms in principle can have a hyperfine structure that is complicated, but I'm going to apply a magnetic field such that the cycling transition is selected. And because of the geometry, these atoms are not going to leave these two level subspace. This is very important. Okay, so now I'm gonna look at the decay rates of my jump operator. So I just have to diagonalize this simple n by n matrix. And this is how these decay rates look like. So this is the operator decay rate normalized to the spontaneous emission rate. This is a function of the distance between the atoms, okay? So you have to think now, if I make any vertical cut here, I have 10 different operators with 10 different decay rates, and they are colored in lines that represent actually wave vectors. So as I mentioned before, for an infinite chain, one can diagonalize things in terms of block waves. So for an infinite chain, these jump operators carry a phase, okay? And this is what is depicted in the plot here on the left. And so the interesting thing in 1D geometry for this polarization is that there are sudden jumps in how radiative are these jump operator sudden changes. And this is related basically with, well, they come from lattice sums that, have 1 over r, like very long range terms, and this results in these peaks. Okay, so as we can see for a given distance, we have a bunch of dark states and a bunch of bright states. In the case of distances approaching or below this critical distance, lambda over 2, then we have a lot of very dark states and some very bright states. Okay, so then one thing that is important to understand is that jump operators are directional. So if I apply a jump operator on my fully inverted state, this will produce radiation, and this radiation is correlated with this kind of wave vector of my jump operator. So this is true even for finite chains. So a finite chain, you cannot use a block wave, but it can be, the jump operator can be well characterized by a wave vector, okay? So even already for 10 atoms, this is quite reasonable. And so what you see here is that, so we're looking at the most subradiant state here at distance 0.9. And this means this jump operator has an intensity profile, a radiation profile that is determined by having a peak at theta equals pi halves. So it's gonna radiate perpendicular to the array. This same arrangement of phases produces a very different intensity radiation when the distance is 1.1. So basically, this actually can be calculated analytically, and we can find the peaks of emission after jump operator action analytically. And this is exactly just like classical phase arrays antennas. So this brings me to, I think, my favorite slide, which is this. So I just found out that the opportunity of putting German radar of 1944 in a slide, so I didn't want to waste this opportunity. And the connection is that basically in the single excitation manifold, these lines of dipoles are really, they really behave like classical antennas. There is no difference. And so you can, electrical engineers have known this since at least 1944. And so they build it for radars. And nowadays in photonics groups, they use this for LiDAR, for instance. So they place chips that they fabricate, and they can tweak the phases between the different emitters. And this makes this radiation is gonna, makes it directional. So it's using these laws and this directionality that I was mentioning before. So by imprinting this phase, they can move the beam, and they can use it. For instance, they can put this on top of a car, and they can see, the car now can see if there are obstacles. So this is a beautiful picture, courtesy of the Lipson group at Columbia. And so in the case of atoms, they are probably the smallest phase array antennas. But this is true for a single excitation. So what happens when you have multiple excitations? Then this is very, very quantum is completely different from these classical phase arrays. And so what happens when you have all the atoms inverted is the following. So as I've mentioned, Dicky told us that the photon emission rate has to grow, and there's going to be a superradiant burst as a function of time. So this is what we see here. So this is for distance equals 0. We see a peak. This is for 8 atoms. Then what happens when we now take our atoms that are at a point and we extend them into an array? What we see is that this superradiant burst starts to, decay. It happens earlier, and eventually it completely disappears after some distance. And so let's try to understand why this is. There has been a lot of controversy about this, whether it comes from the Hamiltonian interactions, dipole-dipole interactions, and so on. And so our understanding is that it comes from a competition between different jump operators. So let's first study the case of Dicky. So in Dicky's case, when all atoms are in the same location, there is only one bright jump operator that is symmetric. And so in the right, we have this plot that is a bit complicated, but I can explain. So this depicts the action of jump operators. So initially we have all atoms in the excited state. As jump operators act, photons are going to be emitted, and eventually we're going to go to the ground state. The jump operators are depicted by these circles, and they go from most radiant to least radiant. And how radiative they are is color coding. So here we only have one bright mode, that is white, all the others are dark. Means that the rate of action is 0. They never participate. So in this case, what we're seeing is a collection of 1,000 trajectories. And basically the width of this line tells us how probable is that these jumps are acting. So you see that all the trajectories follow the same path of action of jump operators. So in this case, there is only one jump operator. There is no competition between them. So what happens when we now extend the array? So what happens now is that jump operators, some of them become bright. And so they are not all dark anymore. And as you can see now, again, like most of the jump operator that keeps us acting is the most bright. But still now we have some competition by the other jump operators that are similarly radiative. So now we have some competition, and this produces actually dephasing. And when we have now an even larger distance, what happens is that now most jump operators are as radiative as each other, which means that the rate of action is like all of them more or less act at the same rate. And this produces the suppression of the superradiant burst. So one can calculate which is the probability of 2 successive jumps from the starting in the excited state. And so it's this equation here. And so this gives this solution. So we have one is not really important. We have a fermionic correction that tells us that we cannot place 2 excitations in the same atom. They have to be distributed in the array. And we have this delta nu. So nu and mu means which kind of jump operator is acting. So this means that operators are enhancing their own action. So keep in mind that this is a process of a spontaneous emission of radiation, but jumps stimulate themselves, but not others, just themselves. And so in some sense, it's a process of self-stimulated radiation. So whenever a jump occurs, it produces this, imprints this phase on the atoms, that promotes the same jump operator to act again. If a different jump operator acts, then this is going to produce dephasing because the phases now are going to be random. And so this means that synchronization either happens at the beginning or it doesn't happen at all and the atoms dephase. So this is exactly what happened here, right? So either it happened at the beginning or it doesn't happen. So this means that we can predict the presence of the superradiant burst by looking at early stage dynamics. So in general, this is a problem that is very hard. It's again like 2 to the n Hilbert space, but just by looking at the early stage dynamics, we can find out whether the superradiant burst is going to survive. So we do this by truncating the Hilbert space to having up to 2 holes. So now our Hilbert space is going to be all atoms excited -1, or all atoms excited -2, meaning the array has emitted up to 2 photons. And with this, we can already predict the slope of these early dynamics. And this is what we found. So we found a crossover between a region where there is a burst and a region where the burst is lost as a function of the distance. And for this perpendicular polarization, this happens around 0.25. So this is hopefully a distance that people eventually can access in experiments. And this means that this gives us predictive power also for looking at other geometries. So this has been a controversy for a long time, whether superradiant burst is gonna survive, and maybe it's a good way to look into these problems. Okay, so then if maybe you don't want to build an array with a distance of 0.2 lambda between the atoms, maybe there are other things that you can still do as an experimentalist to look at signatures of many body physics in collective decay. So because this is correlated dynamics, the photon emission is of course correlated. And as I've said, it's directional because jump operators are directional. So as I've mentioned before, there are these sharp jumps in the decay rates at distances that are half a wavelength, 1 or 2 or 3 and 4 and so on. So if now you have an array with interatomic separation of 0.9 lambda or 1.1 lambda, you should see significant changes in the emission, in the intensity. And this is precisely what you see. So this is the intensity as a function of the emission angle. And as all the dynamics starts occurring, different jump operators are acting at different rates. And because of the directionality, the late stage dynamics, the subradiant state of the dynamics is very different. And photon emission, as I've said, is correlated. There is a lot of bunching. So because again, the photons are trying to, jumps are enhancing each other. And so this is the 2 photon correlation at the same emission angle. So we're putting a detector in the far field that is detecting at some given angle theta, but you could do cross correlation at different angles. And there is correlations there as well. Again, because jump operators are directional, but also multi-lobe. So you could, emit in this direction, but also be correlated in emitting into another direction. And so this, hopefully, people can look in an experiment soon. So with this, very quickly, I just wanted to mention that there is another possibility for many body physics in arrays that doesn't involve multiple excitations, but that involves multiple ground states. And this physics is very complicated, and I'm happy to talk about it maybe during the questions. I can explain how this works. And with this, I have arrived to the outlook. I just think this is fascinating because it's really a problem of many body physics with long-range interactions. But it's also a playground for multidisciplinary physics, where many different degrees of freedom are involved. And so, because I think later we have a discussion, so I wanted to put forward some ideas. As I've mentioned before, well, why do I do chains, or why am I working on chains? I think 1D is unique in some sense, but also it's because it's the kind of easier thing to understand. So I think going to higher dimension is definitely interesting because you can engineer richer dispersion relations, and the sky's the limit. I think compared to dielectrics, one interesting thing of these atomic arrays is that one can imagine to realize coherent control of single photon states. So one can do maybe dynamical dispersion engineering using dressing fields that are going to change the band structure in time as polaritons propagate. I think an interesting thing that we could discuss is like what's the physics of photon-photon interactions and what is the potential of this for gates. And one thing that I'm also interested about is on this process of many-body decay and superradiance, how can we go to higher dimensions and other geometries like rings and spheres that have been controversial historically. And so I think with this, I'm done, and thank you so much.
Okay, so we have a whole bunch of questions for you, Anna. Two questions specifically about the implications for quantum computing, I guess, in the context of this idea that you get exponentially reduced decay. So Avi asks, the possibility of realizing a conditional phase gate using atom arrays is quite interesting. Do you have any insights into how the performance and experimental feasibility compares to prototypical Dwan-Kimball schemes?
So the right answer is no, I don't have it. I mean, I hope to have it. Right now, I don't have it. I can comment a bit on this, maybe inspired at least by the question. So these conditional phase gates, they were suggested in like the 90s, and they were assumed to be happening in like medium with kernel linearities. And then a few years later, they were debunked. And it's easy to demonstrate that they cannot exist when the interaction is local. But in this case, interactions are non-local. So in principle, one can overcome this kind of no-go theorem. And so we have some preliminary calculations that show that, that you can accumulate a certain phase. The phase that you accumulate seems to approach pi only in the case where the distance tends to 0. This is also the case where the loss tends to 0, which is good, but it's also the case where experimental is the least feasible. Still, I think you can acquire a very significant phase at finite distance. The issue also that I should mention is that when the distance is larger, the bands tend to be flatter, so the dispersion tends to be bigger. And so as the photons propagate, they are going to distort. And then there is the never-ending problem of disorder in 1D. And this is an issue for change in general. So I think it's very, like right now it's kind of open. I'm interested in understanding the physics of this, but I don't have the answer of what, like I cannot, tell you that these gates are gonna be the future because I really don't know. It's something we're working on.
Okay, so maybe I'll just paraphrase this second question. It's also about these logic gates. The question is, could you achieve gates with two arrays next to each other and seeing one affect the subradiance properties of the other? And I guess maybe just more broadly, is this something you've thought about, two 1D chains? Yeah,
so I think one of the ingredients for doing these condition phase gates is that the photons only interact once. So to have like photons that are co-propagating, it's hard, but like if you could imagine with two arrays, maybe there is a potential for like co-propagating photons that they acquire phase as they propagate, but they don't collide. So it's again something I've been thinking about, but I don't have like the answer now.
Thank you. Okay. Didi Liebfried asks, should one think of the superradiant burst occurring or not as a phase transition? Is there a relation to percolation thresholds?
Wow, okay, maybe. So that's a good question, I think. So this is kind of new, and I think it's not, in the case of 1D, it's not a transition, it's a crossover. Like there is nothing sharp happening. In other dimensions, it might be, that I don't know. With respect to percolation, like honestly, I haven't thought about this, but it's true that these plots of the like jump operators acting are very suggestive of a network, and maybe one can think about percolations. Right now, my understanding of it is just a matter of competition, and then basically what happens is that if you have multiple jump operators, it's like you have a resource that is you have this energy that you have to release. Like you have your rate n gamma 0. So if you spread it over many modes, then this is not efficient at all. So as you make your chain, you make it bigger and bigger and bigger. There are more and more operators that fall inside the light cone. And then this is like spreading out your energy. And this is why Superradiance kind of dies. But it's potentially, maybe it's, I think it's a very good question. Like maybe percolation is a good way to look at it.
Okay, let's see, what's the next question here? Ivan Deutsch asks, what happened to the real part of the Green's function in the case of collective excitations? Was this integrated into the Hamiltonian?
Yeah, so for sure, this is also a very good question. So in the case of decay, this is completely switched off, so 0. But in the case of the 1D array, of course it happens. It's just that here we're depicting like the action of the jump operators, but in between jump operators, there is coherent evolution that is carried by the Hamiltonian. And then one could imagine, I don't think this is possible, but one could imagine, so kind of my selling point of this is, okay, by looking at the early dynamics, we're good to go. Because we can look at this, how these two photons, these two jump operators enhance themselves, coming from this initial state that is all atoms excited. And from this, we can learn enough to predict. What could happen is that, what if now you have initially decaying kind of photon emission rate, and eventually the Hamiltonian, so the jump operators are not going to rephase anything, but the Hamiltonian magically rephases the whole thing, and then there is a huge peak. So I think this is not possible. I have reasons to believe this is the case, but definitely the Hamiltonian is doing things on its own. Actually, I think Carmichael has a nice paper on, what are, if you include Hamiltonian or not, the Hamiltonian part or not in the dynamics, and how this changes the dynamics. And basically Hamiltonian tends to destroy things even further. So it produces further dephasing. Yeah. But we included that, yeah, for sure.
Fantastic. Okay. So Steve Harris has asked a question, which I guess is sort of related to these quantum computing questions that were asked earlier, but he's asking in the context of photons. He asks, a long-standing problem in quantum optics is, can a single photon cause a pi phase on another photon? EIT and slow light come close but fail. Does your array of atoms, all with EIT, accomplish this?
I think no. So it accomplishes it in the limit of distance equal to 0.
Okay. Okay, well, there are a whole bunch more questions from a whole bunch of people. What I would encourage folks to do, if they have additional questions, is join us for a discussion afterwards with Anna. If you could stop sharing your screen for a moment.
Oh my God. Okay, this good.
Yeah, let's do this first. This is important.
I'm like the worst speaker ever. Sorry, do you give me 1 minute to give the acknowledgement? This is so horrible. Okay, so I should have maybe started by this. I like to acknowledge, of course, everybody that did the work, in particular my postdoc, Stuart Mason. And he worked extremely hard on both the paper on the atomic waveguide and also the recent paper on Superradiance. And this last paper we've done in collaboration with Antoine Brouet and Igor Ferrier-Barbout at the Institute of Optics, Institut d'Optique in Paris-Saclay, and with Professor Luis Orozco at the JQI Maryland. Yes, I hope I will never forget to show this slide ever in my life. Okay, thanks. Now I can stop. Okay.
So if you could stop sharing so that I can share for a moment, that would be great. Okay, so where is PowerPoint? Yeah, this is always the challenge. Where did PowerPoint? Oh, there it is. Great. Okay, so the quantum science seminar is on break next week, but we will be having Jun Yi from JILA and CU Boulder telling us about quantum gas of reactive molecules, evaporation, collision, resonance, long lifetime. And that'll be at our normal time, Friday, August 28th at 12 noon Pacific. So let's thank Anna one more time for just a marvelous, really engaging, fun talk. And please join us for the discussion afterwards if you'd like. The link should be in the Zoom chat.